We'll wait 2 more minutes for others to join. I think we should start the class then. Mm, So, welcome to the week 9, that is week 9 of problem solving session of heat transfer course, whose prime instructor is Professor Sunando Dasgupta at IIT Kharagpur, and myself Kalpita Nath, and I am your presenter here for your problem solving session, and I am research scholar at IIT Kharagpur, for whoever have joined you. So, um, I'll scroll down with today's session. Previous day was also like based on heat transfer question solving of heat exchanger. So there were 3 questions being shared previous day that because of the time constraint we were unable to solve. So I'll share those questions first. Just one second. I'll share those questions first, and we'll try and solve them, and then we'll go with today's problems. So this is the first question for previous day that we were unable to solve because of the time constraint. So have a look at the question. So there is a feed tube cross flow heat exchanger and hot exhaust gases, not liquid. Gases entered at 300 degrees Celsius and leave at 100 degrees Celsius. Are used to heat pressurized water at a flow rate of 1 kg per second from 35 to 125. So the cold fluid is water that is entering at 35 degrees Celsius and leaving at 125. And the hot fluid is the hot exhaust gas that is entering at 300 and leaving at 100 degrees Celsius. The overall heat transfer coefficient is given as 100 watt per meter square Kelvin, and it is based on gas side surface area. Okay, so what we need to find, we need to find the gas side surface area, that is AH. That will be based on the equation like that we just one sec, that we have already studied in class, and we will be using NTU method for that. I think sir have already taught you in the class. Like this week, they sir have already taught you the NTU method. So have a look at the question. The schematic diagram is already represented in the question itself, and also the curve that we need to use for finding the epsilon is also, that is the effectiveness, is also given here. So if we can find C mean upon C max, like depend based upon the C mean and C max and the NTU also we can calculate. So based on that we can easily calculate the effectiveness, right? Okay. Here effectiveness we will calculate, and based on effectiveness and C mean and C max, that is the heat capacity ratio, we can calculate the NTU, and based on NTU we can calculate the surface area. So the problem solving flow will be, first we will calculate, like for calculating the surface area, the final approach is to calculate the surface area by NTU method. So for that we need the number of transfer units, that is the NTU, and for NTU we can use this graph that is provided to you, and for that that will give us the that will need the capacity ratio, heat capacity ratio, and the effectiveness. So effectiveness, we can calculate the heat, the actual heat transfer to the maximum heat transfer, so that we can easily calculate from the temperatures given and the heat capacities of the hot and cold fluid, right? Any doubt? Anyone is having any doubt? Okay, I'll take you are having no doubt, so you can solve it. I'll give you 5 minutes for solving this, and then we'll carry out with the solution. The diagram is clearly visible, right? Just one second. Hello? I'm audible, right? Hello?
Yes, ma'am.
Okay. So the diagram is properly visible. You can see the diagram because that will be required for calculating the NTU. Okay, I'll take that. You can clearly see that. So I'll give you 5 minutes for solving this. We have three questions that were left unsolved for the previous day. This is the question number one, and then we'll go on with the today's question. Today's question is also based on heat exchangers, double pipe and shell and tubes. You can solve this, right? Let me mark your attendance. You are solving, right? Are you guys solving? Anyone there?
Yes, ma'am.
Okay, okay. If you'll be facing any doubt, do ask me. I'm here only. Has anyone solved it? Or should I proceed with the solution? Okay, I'm proceeding with the solution. Okay, so first of all, we will be like from the graph we can easily calculate NTU because effectiveness, everything, the temperature and everything is given, so effectiveness we can calculate, right? And if effectiveness we can calculate, then like effectiveness we can calculate, we can use effectiveness and the capacity ratio, heat capacity ratio to calculate the NTU. So we'll do just 1 second, I'll be back. Yeah, hello. Yes. So I was explaining. So first, to calculate the heat capacity ratio, I need the minimum heat capacity and maximum heat capacity. So let us calculate the minimum heat capacity. As we can see, like minimum heat capacity will be of the cold fluid. So minimum heat capacity will be, this will be 1 kg per second into 4197 joule per kg Kelvin. So this is equal to 4197 watt per Kelvin. Okay. So uh, see now mh is not satisfied, that is the flow rate for the hot fluid is not satisfied, specified. So see, we need to obtain heat capacity ratio of the hot fluid, sorry, heat capacity of the hot fluid. So for obtaining that, we need to do energy balance first. So for energy balance, what we need to do, Q is equal to mh dot cph th in minus th out is equal to mc dot cpc tc out minus tc in. So this will be, from here we can easily calculate cph. So cph will be mh dot cp mh dot cph. This is capital, okay. So this is cc cpc into Tc naught minus Tci upon Thi minus Th, temperature difference. Okay, so CPC is for the water, the cold fluid. So this will be 4197. This is 125 minus 35 upon 300 minus 100. So this is 1889 watt per Kelvin. So this is equal to C mean. So this is equal to heat capacity of minimum heat capacity. So this is okay. So okay. So the hot fluid heat capacity will be the minimum. So now the maximum heat flow that is required for calculating the effectiveness can be found out by minimum heat capacity, that is C mean, into the maximum temperature difference. And what will be the maximum temperature difference? The inlet temperature of the hot fluid and the inlet temperature of the cold fluid, that is the maximum temperature difference. So THI minus TCI. If you are facing any doubt, like if you are not understanding what I'm explaining, interrupt me and unmute yourself and ask me the question. Okay, because I am just also solving on the way, so I may be mistaken somewhere. So if I am mistaken somewhere, like if I'm saying something wrong, do interrupt me and tell me. Okay, so minimum heat capacity is 1889 as we have calculated here. So this is watt per Kelvin. 300 minus 35 degrees Celsius. 5 into 10 to the power 5 watt. Now, actual heat transfer, this we can easily calculate from this equation, right? Anything we can use, as we have all the requirements there. So heat transfer, actual heat transfer rate will be Cc Tc naught minus Tci. So we are using for cold fluid. So this is 4197 watt per Kelvin into 125 minus 35 degrees Celsius. So this is 3.78 into 10 to the power 5. So what is effectiveness? Effectiveness is equal to Q upon Q max. This is Q actual. Okay. So Q actual is 3.78 into 10 to the power 5 upon 5 into 10 to the power 5. So this will come out to be 0.755. Who have doubt till now? Like, are you having any doubt in understanding what I am solving here?
No, ma'am.
Okay then. So after that, again, what we need, like I have already I always tell you what we need finally. So for any question, if we plot a roadmap, like how we need to solve, what we need to solve, and what we require for that, then it will be easier for you to understand the roadway, and it will be faster for you to solve that question. So now we have been provided with the graph and we need NTU. So effectiveness were calculated, and another thing that we need for calculating the NTU, that is number of transfer unit, is C mean upon C max. So C mean upon C max, that is the heat capacity ratio. We denote it as CR. This is 1889 upon 4. 1 second. Just 1 second. Sorry. This is 4197, and this will be what? This will be 0.45. Okay. So now if we will get from the graph, if you will see, just let me maximize the graph first. Okay, so if we will go for heat capacity ratio of 0.45, heat capacity ratio of 0.45, this is somewhere between like close to 0.5, but just a bit less than that. So the top one is 0, then it is 0.25, so it will be close to 0.5, right? It is 0.45, so it will be close to 0.5. So here okay, just 1 second. Here So from here, what we have? We have effectiveness of 0.755, 0.755, like this. 0.7, 0.7, 0.6, then 0.7, 0.75 means in between 0.7 and 0.8. So here, and this will be close to the third line. So this will come approximately NTU2. So are you getting that? Hello? You just have to take the curve. What is the curve for capacity ratio? And then you have to point out from effectiveness. Okay, so like let me draw some one straight line, then it will be easier for you. So from 0.75 means approximately up till here, and this will be close to this, right? The line is visible, right? This line. Yeah. So if we will extend this to NTU, it will be approximately 2, right? Okay. So NTU will be 2. We found out from the graph. So NTU is 2. Now, what is NTU? We already know. 1 second. NTU means overall heat transfer coefficient into heat transfer area into minimum heat capacity. So this is 2. So the heat transfer area will be 2 into C minimum, that is 1889, sorry, 1889, and upon 100 watt per meter square Kelvin. So this is 37.8 meter square. Okay. So this is our answer. Are you able to understand? Anyone is having any doubt?
No, ma'am.
Okay, then I'll proceed to the next question. Okay. So this is also previous classes question. So over there, steam is passed through a setup of a condenser of a power plant, and is to be condensed. That is to be condensed at a temperature of 30 degrees Celsius with cooling water from a nearby lake. So cooling water is entering at 14 degrees Celsius and leaving at 22 degrees Celsius. The surface area of the tube is 45 meter square, and the overall heat transfer coefficient is also given as 2100 watt per meter square degree Celsius. Determine the mass flow rate of the cooling water needed and the rate of condensation of steam in the condenser. This is very easy, and properties are also given here. Remember, it is condensation, so there will be like the heat transfer when we'll be calculating on the steam side, it will be with respect to condensation, that is it will be not mcp delta t, it will be m into heat of vaporization, right? So how we will approach this? Anyone? We are being provided with the heat transfer area, we are being provided with the overall heat transfer coefficient. So what we need the log mean temperature difference, right? So how we will get log mean temperature difference? We just need one temperature is left to be known, right? So Okay, so okay, yeah. So the steam is will be at same temperature. That is, steam is entering at 30 and leaving at 30. Because here it is like phase change is going on. So temperature will be constant. So what we need now for log mean temperature difference calculation, every like temperatures are already given. Delta T1 and delta T2. So delta T1 we need to calculate, that is TH1 minus TC naught, right? TH1 minus TC naught. So TH1 is 30 and TC naught will be, that is TC naught means the outlet temperature of the cold fluid. So this is already given as 22. So this is delta T1, and the other one, that is TH out, that is also 30 degrees Celsius, and TC in is 14 degrees Celsius. That is also given. So delta T2 also we can calculate. So from that we can easily calculate log mean temperature difference, and if delta T log mean temperature difference we can calculate, then we can easily calculate the heat transfer, rate of heat transfer. So rate of heat transfer through the heat exchanger, here heat exchanger is working. From that we can that will be is equal to, as I already told, here like change of phase is taking place. So uh, m and क्या बोले enthalpy. Okay, so this will be mass flow rate into enthalpy, and from there you can easily calculate the rate, what is required next, mass flow rate. Okay, mass flow rate of the cooling water. So mass flow rate of the cooling water heat, the rate of heat transfer you have calculated, and from the rate of heat transfer Cp delta T also you know. So from there you can easily calculate the rate of cooling water. Okay, so if we can easily calculate the rate of cooling water, and also the flow rate, like rate of cooling water, you can calculate the enthalpy is already, like heat of vaporization is already given 2431. So from that you can easily calculate the rate of cooling, mass flow rate of the cooling water. Okay, let me give you the equations. Like first we'll calculate Q, right? Now Q is equal to, for cooling, for cold fluid it is mc cpc tc naught minus tci. Now as phase change is taking place on the other side, so here what will happen, it is mh into heat of vaporization, that is fg, that is already given here 2431. Okay, so here this we can easily calculate from overall heat transfer coefficient, and area of heat transfer is also given, and delta T log mean temperature difference. So from here we can easily calculate. So if this we will calculate, and this we already know. So this we can easily calculate. Are you having any doubt in understanding? I think now I am able to make you understand what I wanted to say. Are you having any doubt? Okay, I'll give you 2 minutes for solving this. I've already told you how to solve. Just solve this, and we'll discuss the solution then. I don't think you are able to solve this, so let me solve it for you. So first we need to calculate log mean temperature difference. For that we need to first calculate delta T1. So as we already know, delta T1 is the TH, like THI. Okay, TH naught. This is similar. This is same. This is cooling liquid. TCI, TC naught. So this is delta T1. This is delta T2. THI minus TC naught is delta T1. Delta T2 is TH naught minus TCI. Okay, so this is 30 minus 22, and this is 8 degrees Celsius, and this is 30 minus 14 is equal to 16 degrees Celsius. Okay, so now log mean temperature difference is delta T1 minus delta T2 upon ln delta T1 by delta T2. This is 8 minus 16 by ln 8 upon 16. So this will come out to be 11.5 degrees Celsius. Now rate of heat transfer is equal to UA delta T ln. So this is given as 2100 watt per meter square degree Celsius, and this is 45 meter square, and this is 11.5 degrees Celsius. So this is 1.087 into 10 to the power 6 watt. Say this is 1087 kilowatt. Now K is equal to MC CPC TC naught minus TCI. So we have already calculated this. Now the next work is what we need to find out. We need to find out the mass flow rate of the cooling water and the rate of condensation of the steam in the condenser, right? So mass flow rate of the cooling water means MC dot. So MC dot we need to calculate. So MC dot is equal to Q upon CPC TC naught minus TCI. So Q is already given as 1087 upon joule per second upon 4.184 kilojoule per kg degree Celsius, and this is 22 minus 14 degree Celsius. So this will come out to be 32.5 kg per second. Now again another thing that is required to find out is rate of condensation of steam. So for rate of condensation of steam, we already know that Q is equal to, we can also write as the mass flow rate, the rate of condensation of steam into the uh, the uh, heat of vaporization, this one. Right. So this we need to calculate. So ms dot will be is equal to Q upon HFS. This is what? This will be 1087 upon, what is this? This is 2431 kilojoule per second, kilojoule per kg. Right. So this will come out to be how much? This will come out to be 0.45 kg per second. So this is the answer for this question. Let us proceed to the next question now. A 2 shell pass and 4 tube pass heat exchanger is used to heat glycerin from 20 degrees Celsius to 50 degrees Celsius by hot water. Okay, so now which enters a thin wall 2 centimeter diameter tubes at 80 degrees Celsius and leaves at 40 degrees Celsius. The total length of the tubes in the heat exchanger is 60 meter. The convection heat transfer coefficient is 25 watt per meter square degree Celsius on the glycerin shell side, and heat transfer coefficient, the heat transfer coefficient is given on the glycerin side is also given, and on the water that is tube side is also given as 160 watt per meter square degree Celsius. Right, these are the heat transfer coefficient, not the overall heat transfer coefficient. So from this heat transfer coefficient we can easily calculate the overall heat transfer coefficient by including the correction factor. Right. Now determine the rate of heat transfer in the heat exchanger before any fouling occurs, and if the fouling occurs and the fouling factor is 0.0006 meter square degree Celsius upon watt occurs on the outer surface of the tube. So for the two cases we need to find out. So I'll give you 2 minutes to solve this and then we'll proceed with the solution. I'll be right back in 2 minutes. So let us solve this question first. So first, okay, so the length and dia is already given here, so we can easily calculate the surface area, heat transfer area, right? Just one second. So the heat transfer area is pi dl is equal to pi into 0.02 meter into 60 meter. So this will be 3.77 meter square. So the rate of heat transfer is equal to, we already know UAS, that is the overall heat transfer coefficient, the surface area, the heat transfer area. The here for fouling we also need to consider the fouling factor and the log mean temperature difference, right? So the log mean temperature difference, for log mean temperature difference we need delta T1 and delta T2, delta T1 minus delta T2 upon ln delta T1 upon delta T2. So delta T1 is THI minus TC naught, we already know this. So this is 80 minus 50 is equal to 30 degrees Celsius, and delta T2 is equal to TH naught minus TCI. So this will be 40 minus 20 is equal to 20 degrees Celsius. So this will be 30 minus 20 upon ln 30 upon 20. So this will come out to be 24.7 degrees Celsius. Now we have already been given, for the correction factor we need to find out P, that is the heat P and the heat capacity ratio. So heat capacity ratio we can easily calculate from the minimum upon maximum heat capacities, and we need to calculate the P. So P and R we need to calculate. So R is equal to T1 minus T2 for hot fluid, and T2 minus T1. So this is 20 minus 50 upon 40 minus 80. This is equal to 0.75, and the uh, P, that is the temperature difference between the cold fluid and the maximum temperature difference. So the maximum temperature difference, this is basically can be found out to be T2 minus T1 for the cold fluid and the maximum temperature difference. So this is equal to 40 minus 80 upon 20 minus 80. So this is 0.67. So for 0.67, let me maximize this. If R we take as 0.75, R 0.75 means here, approximately here, close to 0.8. So R 0.75 and P will be 0.67. 0.67 means here approximately. So 0.67 means, okay, here, point here, 0.67 means 0.65, this is 0.65, and approximately this will be 0.67. So this will be approximately here. That means, let me draw a line here. So R is sorry, P is 0.67. 0.67. 0.67 means here. And this will go up to 0.75. That means here approximately. So this will come close to 0.91. So the correction factor will come about 0.91. So in case of no fouling, first of all, in case of no fouling, the overall heat transfer coefficient is equal to 1 upon Hi plus 1 upon H naught. That is the heat transfer for both of the hot and cold fluid side. So this will be 1 upon 25 plus 1 upon 160. So this will come out to be how much? This is 21.6. So the rate of heat transfer will be 21.6 into surface area is 3.77 into friction factor, the correction factor is 0.91 into the log mean temperature difference is 24.7. This is 1830 watt. Now it is said that after fouling we need to also consider the fouling factor. So for that the overall heat transfer coefficient will change. So this is H naught plus Hi plus 1 upon plus friction fouling factor. So the resistance for fouling factor, so this is 1 upon 160 plus 1 upon 25 plus 0.0006. This will come out to be 21.3. Again Q will be same 21.3 into 3.77 into 0.91 into 24.7. This will come out to be 1805 watt. This will come out to be 1805 watt. Okay. So this is what has been asked to us. The heat transfer rate for both of the cases we have found out. So now we'll proceed to today's question. So this is the first question for today's session. So in this question, what is being said? There is a cross flow heat exchanger, and the it is for cooling blood. So I have already done two same question, but he have asked you to calculate something else. So that also you need to calculate here, and the next part of this to calculate the effectiveness. So for that, first of all, we need to calculate the two parts that sir have already taught you in the class. So first thing is that the hot fluid is entering at 37 degrees Celsius and leaving at 25, and the cold fluid is entering at 0 and leaving at 15 degrees Celsius. So it is said that the body is introduced, basically the blood is introduced to hypothermia, and by using ice water. So obviously the ice water temperature will be 0 degrees Celsius, but the temperature will be gradually increasing if it will be in contact with the blood. So this temperature will increase at 15 degree, up to 15 degrees Celsius. And we have to assume steady state condition, and overall heat transfer coefficient is also given as 750 watt per meter square Kelvin. Now, overall heat transfer coefficient remains constant with water flow rate changes and constant properties. Now, given data is for water density and heat capacity is given, and for blood also is given, and we need to find out the value of effectiveness. So I'll give you 2 minutes to solve this, and then we'll proceed with the solution. So let me give you the road play for that. So for effectiveness, what we need to find out the actual heat transfer to the maximum heat transfer, right? So for the maximum heat transfer, we need to know which of the heat capacity is minimum, and then we need to calculate the minimum heat capacity and the temperature difference between the hot fluid inlet and the cold fluid inlet. That is the maximum temperature difference. Now for that, first of all, the mass flow rate of hot fluid, like already the volumetric flow rate of hot fluid is given, so from that mass flow rate of the hot fluid can be calculated. Now if we calculate Q from that, because Cp is also given for the hot fluid, that is the blood. So Cp is given, the mass flow rate is given, and the temperature difference is also given, so we can easily calculate the rate of heat transfer. So if we will calculate the rate of heat transfer, then from there we can calculate the mass flow rate of the cold fluid, and from the mass flow rate of the cold fluid we can calculate the volumetric flow rate for the cold fluid, right? Now once mass flow rate for the cold fluid we calculate, then the heat capacities for both hot fluid and cold fluid we can calculate, and we can easily compare which of them is minimum, and from there we can calculate the maximum heat transfer, and obviously the rate, the actual rate of heat transfer we have already calculated earlier. So from there we can easily calculate the effectiveness. So I'll give you 2 minutes to solve this. I'm here only if you are having any doubt. The two other or three other students join. I don't know why they left. So okay, one only Tushar is online. So you please solve this. I have already explained to you. If you are having any doubt, then unmute yourself and ask me the question. Okay. So what do we need to do about this? First of all, as I've already told you, that first we need to calculate the uh, like we already have been provided with the volumetric flow rate of the hot fluid. So from that we can easily calculate the mass flow rate of the hot fluid. So volumetric flow rate is given as 5 liter per minute, right? So from there we can calculate the mass flow rate of hot fluid, that will be 1050 kg per meter cube into 5 liter per minute into 1 minute upon 60 second into 10 to the power minus 3 meter cube per liter. So this will come out to be 0.0875 kg per second. So the rate of heat transfer will be mh dot ch thi minus th naught, because we already have everything for to calculate the heat transfer rate from the hot fluid. So we can easily calculate that from the hot fluid conditions. So this is given as 0.0875. We have calculated that kg per second into the heat capacity. Heat capacity is 419, sorry, for the hot fluid, right? 3740. 3740 joule per kg Kelvin into 37 minus 25 Kelvin. This will be 3927 watt. So now we need to find out the the mass flow rate. Volumetric flow rate we don't need. Sir, I have taught you in the class, right? Over there, volumetric flow rate we needed to calculate. So here, as we just need to calculate the mass flow rate, we'll calculate that. So we need to calculate the mass flow rate of cold fluid. So for that, Q is equal to also mc dot CPC TC output minus outlet minus TC inlet. So this is 3927 is equal to mc dot into 4198 joule per kg Kelvin into 15 minus 0 Kelvin. So this is equal to, so mc dot will come out to be 0.0624 kg per second. So just 1 second. Okay, so now we need to calculate the we need to calculate the effectiveness, the value of effectiveness. For this we need to calculate the maximum heat transfer, and for that we need the minimum heat capacity ratio, so minimum heat capacity. So for that, first let us calculate the heat capacity for the cold fluid, that is mc dot cpc. That will come out to be 262 watt per Kelvin, because this is 4198 and this is 0.0624, and CH is for the hot fluid, heat capacity for the hot fluid, mh dot cph is this is 0.0875, and this is 3740. Mm, this will come out to be 327 watt per Kelvin. So C minimum will be this one, right, for the cold fluid. So for the cold fluid, this is 262 watt per Kelvin. So maximum rate of heat transfer is C minimum THI minus TCI. This will come out to be 262 watt per Kelvin. 37 minus 0 Kelvin is equal to 9694 watt. So the effectiveness is Q upon Q max is equal to 3927 by 9694 is equal to 0.405. This is option C. Okay, so let us proceed to the next question now. I hope you have already understood what I have explained here. So this is question number 2. So over there, a steam A with specific heat already given is cooled from that is the hot fluid. It is cooled from 90 to 45 in a concentrated double pipe counter current heat exchanger and have a heat transfer area of 8 meters square. The cold steam having heat capacity of 1000 joule per kg Kelvin enters the heat exchanger at a flow rate of 1 kg per second and at 40 degrees Celsius. So the inlet temperature is given, outlet temperature is not given. So the overall heat transfer coefficient is given, and the mean driving force is based on the arithmetic temperature difference. AMTD, not LMTD. So here we will calculate AMTD, arithmetic mean temperature difference. Now, okay. So the mass, we need to find out the mass flow rate of steam A, that is for the hot fluid. So these are the options given. You calculate this. I'll give you 2 minutes to calculate this, and then we'll proceed with the solution. Okay. Okay. Should we proceed with the solution? I think Tushar is there, but still not there, because you are not responding to me. So I'll just blindly proceed to the solution then. So first, we need to calculate the the AMTD. So for the arithmetic mean temperature difference, so TAMTD will be basically 90 plus 45, that is the TA in 90 plus TA out 45, 2 minus TB in is also given as how much? It's given as, just 1 second, 40. Yeah. So 40 plus out is not given, so TB out upon 2. So we need to find TB out. So MB CPB, if we do the balance, TB out minus TB in is equal to UA T AMTD, right? Cause for the hot fluid mass flow rate is not given here, so we need to use this. So if we use this, this will be 1 into 1000 into TB naught. TB naught is needed to find out, and TB in is 40. So this is 250 into 8 into 67.5 minus 20, minus 20 minus TB out. This one, right? 67.5, this 67.5 minus 20 minus TB out. So if we will solve this, I am not going for the details. So if you solve this, TB out will be you will find out it to be 67.5 degree Celsius. So now MACPA TA out minus TA in is equal to MBCPB TB out minus TB in, or MA into 2000 into 90 minus 45 is equal to 1 into 1000 into 67.5 into sorry, minus 40, right? So we'll get MA from here. This will be 0.305, sorry, not this one, 0.305 kg per second. So this is option C. Now let us proceed to question number 3. Choose the correct statement regarding the definition of the effectiveness of heat exchanger. So we already know this, the effectiveness of heat exchanger is Q upon Q max, that is the actual heat transfer to the maximum heat transfer. This we already know, right? So this is actual heat transfer to the theoretical possible maximum heat transfer. This is option B. Answer is option B. Now let us proceed to question number 4. So a counterflow concentric tube heat exchanger, surface area is given and the overall heat transfer coefficient is given, was undergoing test after a service of extended period of time. The specifications are given, every specifications. Assume steady state condition and negligible heat loss to the surrounding and constant properties. Find the fouling factor, if any, based on the test result of the engine oil flowing at 0.1 kg per second. So the engine oil, there is a hot fluid, have mass flow rate of 0.1 kg per second, and its temperature change from 110 to 66, and the water, that's a cold fluid, in the temperature is 25 degrees Celsius and flow rate is 0.2 kg per second. And the data is the specific heat capacity is also given. So we need to calculate what? We need to calculate the what we need to calculate? We need to calculate the fouling factor. Okay, so I'll give you, I think you don't have any doubt regarding understanding of the problem. Are you having any doubt in understanding the problem? I take it you don't have any doubt. So I'll wait for 3 minutes for solving this, and then we'll proceed with the solution. Okay, so have you solved it? Tushar, are you there or not? Hello? Okay, let's solve with this problem. So first of all, area is already given as 5 meter square. The overall heat transfer coefficient is given as 38 watt per meter square Kelvin. So now, what we need to find out? We need to find out the fouling factor, if any. So, energy balance equation, energy balance, first, for hot fluid, everything is given, like its mass flow rate is also given, and its heat capacity is given as how much? 2166, and specific heat capacity, and temperatures are also given. So this is 110 and this is 66. So this will come out to be, the rate of heat transfer is 9530 watt. Now for cold fluid, this is MCW, MCCPC, TC, TC out minus TC in. So this we know 9530, and this is zero point 0.2, and this is 4178, and this is TC naught minus 25. So from there we can get TC naught. TC naught is 36.405 degrees Celsius. Right. Now the rate equation is Q is equal to UA delta T ln CF. So first we have to check whether fouling, like whether fouling factor is necessary here or not. So obviously heat rate will be same. So this we already know. So this is how much? This is 9530 watt, and overall heat transfer coefficient is given as like first we need to calculate this. So this will be TH in minus TC naught. So this will be 110 minus 36.4 minus 66 minus 25 upon ln 110 minus 36.4, 66 minus 25. So this we have put like this, and area is 5 meter square. So u, let us keep it as it is. So u, if we will calculate from all this, so u will come out to be 34.2 watt per meter square Kelvin. So now u is equal to 1 upon u. Okay, so we have already seen it is 34.2. So obviously the overall heat transfer coefficient, if it's given as 38, so there must be some fouling factor. That's why its value came less than this. So this is UD, overall heat transfer coefficient, plus some fouling factor resistance. So this is 34.2 is equal to 1 upon this, how much? This is 38 plus the resistance. So this will come out to be how much? This will come out to be 0.0029 meter square Kelvin per watt. So this is how much? This is option A. Now let us proceed to the next question. The maximum buffer spacing of a shell and tube heat exchanger should not be greater than the shell diameter. Choose the correct option. Obviously it is true. This is option 5. This you sir have already told. I am not going to the details. Now question number 6 is another problem. So what does it say? A double pipe shell and tube heat exchanger is constructed of stainless steel. Its thermal conductivity is given. The inner tube dia is 1.5 centimeter and outer tube dia is 1.9 centimeter. And an outer shell diameter, inner diameter is the outer shell. Now for the outer shell, the inner diameter is 3.2 centimeter. The convective heat transfer coefficient is 800 watt per meter square Kelvin on the inner surface of the tube, and The convective heat transfer coefficient on the outer surface is 1200 watt per meter square Kelvin. For fouling factor of 0.000004 meter square Kelvin per watt on the tube side, and for the shell side it is 0.0001 meter square Kelvin per watt. So determine the thermal resistance of heat exchanger per unit length. So thermal resistance we need to calculate. The every details for the shell side and tube side are already given. Total thermal resistance, we know just the total thermal resistance will be just the inverse of all the resistances add on, like if we'll add on together. So you can easily calculate that. I hope you remember the formula. Just add on all the resistance that are given separately together. I'll give you 2 minutes for calculating this, then we'll proceed with the solution. Have anyone solved this? I think so. No one is present. Someone is present there. Tushar is present, still not responding. So, if the session is not interactive, then it's not worth. Like if you can just check on other problem solving sessions. Like there should be interactive session. If you are there, please respond. Because previous class also, I think your mid semesters are going on. So previous class I take it you were not there. But today you should at least respond. Right. Okay, so first of all, we'll assume that the heat transfer coefficient and fouling factors are constant and uniform. So the thermal resistance of an unfinned shell and tube heat exchanger with fouling on both sides of the heat transfer surfaces, we can easily calculate by the resistance. We can easily calculate by the following way. So this is inverse of overall heat transfer coefficient. So this is you just one second. This is UIAI 1 upon U naught A naught. This is 1 upon HIAI plus resistance, fouling resistance on the inner side, that is the tube side, and the area for the tube side, plus ln d naught. This is for the conductive. This is for the conductive part, that is for the material of the tube. Uh, so this is the conductive resistance 2 pi kdl. These are the convective resistances, and this is the fouling resistance, conductive resistance on the tube side, and this is the conductive resistance on the tube side. This is the convective resistance on the tube side. This is the fouling resistance on the tube side. Again, for the this is the conductive resistance between shell and tube, right? And depending upon the material that is consisting of the tube. So this is the fouling resistance for the shell side. This is the area of the shell side, and this is H naught A naught. This is the heat transfer coefficient for the shell side and the area for the shell side. That is, this is the convective resistance for the shell side. Now AI for the tube side area, we can calculate pi DIL. This is pi 0.015 into 1. So this is 0.04712 meters square. Right. Now the shell side, this is pi D naught L. This is pi. Just one second. Okay. So this is 1.9 centimeter. So this is 0.019 into 1. So this is 0.0597 meters. Now substituting the above values in the above equation, the total resistance is 1 upon 800 H naught, sorry, HI 0.04712 plus the resistance, the fouling resistance on this side 0.0471, and the conductive resistance 0.019 upon 0.015 into 2 pi 15.1 into 1, 2 pi dl, right? Now just one second. Okay, now for the tube side, for the shell side, this is 0.0001, 0.001, 0001, 0.0597. This is the area, plus 1.1200 into 0.0597. This will come out to be 0.053154 Kelvin per watt. This is the total resistance. Now, how much resistance is offered due to fouling? What we'll do, we'll just add on this. Just let me take some other colored marker. We'll take on this and this. We'll add both of them. So basically, if we'll calculate this separately, this came out to be 0.02653. This came out to be 0.00849. This came out to be how much? 0.002491. This came out to be 0.00168. This came out to be 0.01395. So the resistance due to fouling is 0.00849 plus 0.00168. This one and this one upon total resistance 0.053154. We are just trying to calculate the resistance offered by the different parts to the total resistance. So this will come out to be 19.13%. Now the resistance due to steel tube separating the two fluids, that is the resistance due to conduction. So the resistance due to conduction is equal to the resistance due to conduction or separation is equal to 0.002491. This part 0.002491 upon total resistance 0.053154. This will come out to be 4.68%. Now total is convective resistance. The rest is convective resistance. So this will 0.02653 plus 0.01396 upon total 0.053154. This will come out to be 76.17%. So the convective resistance provides the maximum resistance to the heat transfer. Right. Now let us proceed to the next question. It's already 8:03. We'll solve one more question and then we'll end today's class. And the rest of the question we'll solve in the next week. Okay. So this question number 7 is already connected to question number 6. Determine the overall heat transfer coefficient U, I and U naught based on the inner and outer surface of the tube. So what is the overall heat transfer coefficient for the inner and outer side? This is very easy, right? I'll give you 1 minute to solve this and then we'll proceed with the solution. I think we'll proceed with the solution then. So this is relatively easy. So we already have seen here total resistance is equal to 1 upon UIAI, and this is equal to 1 upon mu naught NO. So from there we can easily calculate UI is equal to RAI. So this is 0.0532. AI also we have calculated 0.0471. So this will come out to be as 399.087 watt per meter square Kelvin, and U naught is equal to 1 upon RA naught. So this will come out to be 0.0532, and this is 0.0597. This will come out to be 314.857 watt per meter square Kelvin. Difference between the overall heat transfer coefficient, like what is the difference between overall the two of the overall heat transfer coefficient? This we can, and the percentage if we need to find out. This we have already found out, so 314.857. So this is option D, right? So now if we want to find out the difference, 314.857 upon 314.857 into 100%, this will come out to be 26.7%. Okay, so now we can do one more question, I guess. So I'll show you this question. This is the last question that we'll do for today. Then others will solve next. Okay, so there is a two shell pass and four tube pass heat exchanger is used to heat glycerin from 20 to 50 degrees Celsius. The cold fluid is glycerin that will that inlet temperature is 20 and the exit temperature is 50. By hot water, so the water will enter at 80 and will leave at 40. There is a 2 centimeter diameter tube as 2 centimeter wall diameter tube as depicted in the schematic diagram below. The total length of the tubes in the heat exchanger is 60 meter, and the convection heat transfer coefficient is also given as 25 watt per meter per Kelvin. The glycerin shell side for the cold fluid side it is 25, and for the hot fluid side it is 160. Determine the rate of heat transfer in the heat exchanger before fouling. Okay, so correction factor is given. Okay. Achha. Now we don't require like correction factor. We can easily calculate. Correction factor we can easily calculate. For that we need heat capacity ratio and the ratio between the cold fluid and the maximum temperature difference. So if we know both of them, we can find out the correction factor. And if we can find out the correction factor, we can easily calculate the heat transfer heat rate of heat transfer. So similar way, we have already solved this type of question. So I'll give you 2 minutes to solve this, and then we'll proceed to the solution. I'll be back in 2 minutes. Okay. Okay, so let us solve this last question. So first of all, it's been asked that first of all we need to find out the surface area. So for finding out the surface area, total length of the tube is given and also diameter is given. So heat transfer area we can easily calculate. So the heat transfer area will be pi d naught L. So this is pi 0.02 into 60, right? So this will this will be 3.77 meters square. Now, the rate of heat transfer will be is equal to overall heat transfer coefficient, the heat transfer area, and the correction factor, because this is shell and tube heat exchanger, and this is the equation that we are using for double pipe heat exchanger. So that's why we need the correction factor for shell and tube heat exchanger, for applying it to shell and tube heat exchanger. So delta T, so log mean temperature difference. Now, log mean temperature difference, for log mean temperature difference we need delta T1 and delta T2. So delta T1 will be T hot fluid temperature in minus T cold fluid temperature out. So this is 80 minus 50 is equal to 30 degrees Celsius, and this is TH out minus TC in. So this will be 40 minus 20 is equal to 20 degrees Celsius. So delta T ln Cf, that is the log mean temperature difference, is equal to delta T1 minus delta T2 upon ln delta T1 by delta T2. So this will come out to be 30 minus 20 upon ln 30 by 20. So this is 24.66 degrees Celsius. And now for calculating the correction factor, we need P. So P is equal to T2 minus T1 by T1 minus T1. This is 40 minus 80 upon 20 minus 80. So this is 0.667. Now the heat capacity ratio, that is T1 minus T2 upon T2 minus T1. So this is 20 minus 50 upon 40 minus 80. So this is 0.75. So temperature difference between hot fluid and cold fluid. Now, if we will use this P and this R, let us proceed to the diagram first. Now, we have R as 0.75 and P as 0.667. 0.667, that means approximately here. Approximately 0.667. 0.667 means approximately here. And R is where? R is 0.75. Means here approximately. So this will come out to be point here. This will come out to be 0.91. Let me increase the weight. So this will come out to be 0.91. Now, if this will come out to be 0.91, then again for the case of no fouling, the overall heat transfer coefficient is U is equal to 1 upon Hi plus 1 upon H. So this is 1 upon 160 plus 1 upon 25. So this will come out to be 21.622 watt per meter square Kelvin. Now the rate of heat transfer becomes Q is equal to UA as F delta T log mean temperature difference. So this is 21.6 into area 3.77 into 0.91 into 24.7. So this will come out to be 1830.35 watt. This is option C. C. This is option C. This is in kilowatt, right? Yeah. So now let us proceed to question number 9. This is the last question. Actually, this is linked to question number 8. So we must solve this. So that will be over with this part of question. So determine the rate of heat transfer in heat exchanger in kilowatt after fouling with fouling factor of 0.0006. The same way we have already done one question of the same type, right? This one question of the same type we already have done earlier. Okay, let's not check that question. Let's be over with this question. So in the same way, we'll be using this in overall heat transfer coefficient, and we'll be calculating the new rate of heat transfer. Right. So I'll give you 2 minutes to solve this. Then we'll proceed with the solution. I'll come in 1 minute. Okay. Okay, so let us proceed with this solution. So in the similar way that we have done in the previous problem, we'll just update with the fouling factor is given. So we'll update with the overall heat transfer coefficient. So overall heat transfer coefficient will be updated here. So this is HI H naught plus RF, the fouling factor resistance. So this is 1 upon 160 plus 1 upon 25 plus 0.0006. So this will come out to be 21.345 watt per meter square Kelvin. So the excuse me. So the rate of heat transfer is given by the overall heat transfer coefficient here, area of heat transfer, the correction factor, and the log mean temperature difference. So this will be similar as earlier. So 21.345 into 3.77 into 0.91 into 24.7. So this will come out to be 1808.74. So what is this? This is option D. Right. Of heat transfer decreases because of fouling. So obviously, as we will compare from here, it have decreased. So obviously this is expected because of fouling, rate of heat transfer obviously will decrease. Okay, so this is it for today. We'll be back with the session on the next week in the same time, that is Tuesday at 7 p.m. to 9 p.m. So I'll end the class here. Bye bye. Okay, uh, just 1 second. I'll show you the questions that are left for today. I'll give you one glance of that. You can take the screenshot, and obviously I'll be uploading the video as well. So the last there are 4 questions left, right? Yes. 4 questions left. So I'll give a glance of that. This is question number 10. There's 11, 12, and there's 13. So I hope you will try and solve this back at your home, and we'll discuss about these questions on the next week. Okay, so bye. I'm ending the call.